Now we will look at statistical dispersion. For example, if I have two data sets, let's say I have 1, 1, 4, and 4. So you have one data set, and here I have another data set, 2.5, 2.5, 2.5, and 2.5. If we calculate average of this data set, it's easy to see that the average is 2.5. And the same, of course, very obvious here. So you see that these two datasets have the same average, but they are very different, because in the first case there are quite a big spread in the data, while in the second one all of them lies exactly at the middle. So if you take an average or some other measure of center, that's not the only relevant interesting information we have about the dataset. It's also the dispersion, how much the dataset spreads. So we want to have measures of that, and we will look at different measures here. The first one we will look at is called the range. And what is range? Yeah, that's a very coarse measure. It just takes the largest data and subtracts the smallest data. So it's the distance between the smallest and the biggest one. So in the first data set we had 4 and 1, so the distance between these is 4 minus 1, so 3. So the range is equal to 3 in this case. In the second example we had the largest one was 2.5 and the smallest one was the same, so the range is 0. So range is very crude. It's just taking the smallest one and the biggest one and looking at the distance between those. Then we also have other measures. The next example of measure or spread is interquartile range. It's also called a mid-spread. Just first to have an intuitive idea of what it is. Let's say we have the data set here, drawn schematically. And then we take the middle of the data set. Then we have 50% here, 50% here. Then I take the middle again of these parts. Then I have 25% in each of these. These points here I call the quartiles. This is quartile 1, quartile 2, quartile 3. In the middle here, between quartile 1 and quartile 3, I have 50% of the dataset. And this distance here, that is what you call the interquartile range. So this is the distance between this and that. So distance between the middle 50%. But this is intuitive idea. To make this a little bit more precise, let's define it exactly. First of all, let's find what is quartile 2. Quartile 2 is the median of the whole thing, the median of the whole data set. So what's that? Yeah, now we have to take a concrete example. So let's take 1, 2, and 3. So what shall we take? So let us do like this. So we have 6 data. What is now the middle of this, the median of this? Yeah, it's here in the middle between 3 and 3. So you have to take the average of 3 and 3. So it's, in this case, quartile 2 is here. So it's 3. Okay, so that's the middle of this data set. This middle quartile, the second quartile, divides up the data set into 2 parts. We have 50% in the lower part, 50% in the upper part. Then we want to find what is the quartile 1, dividing up to 25%. So you have to divide this up into 25%. Then we take the median of lower part. So we take the median of this one, and the median of this one is this. So we have the quartile 2 here, or the quartile 1 here. So this is 2. And same for the third quartile. And what's the median of this? Yeah, it's 4. And now the interquartile range is the distance here. So what's that? So the interquartile range is Q3 minus Q1. So that is 4 minus 3 in our example, 1. So the distance between these is 1. So 50% lies here with a difference in value of 1. So that's a measure of spread here, or dispersion, using the interquartile range. Mean absolute deviation. That is the next measure we want to look at, of the measure of dispersion. It's a very intuitive one, but is perhaps not most commonly used. So how do we define this? If we have a data set, so let's put them here on the number line. So we mark the data with x's here. So x represent 1 data. So let's say we have something like this. And this is a number line, so we could have any numbers here, 0 and whatever, 100. So let's say we have the mean, or the average, somewhere here. Here we have the average. And measure of spread in this case, if we look at each of the data, for example the first one, how far away from the average is it? Yeah, if we call the first one x1, this is the first one, x1, and we take minus the average, then we will get the number. We get the distance here, but we will get with a negative number. If you just take this, we don't want a negative number, we want the distance. We want to remove any signs. And in mathematics, if you put like this, it means to remove any signs of whatever you have in the middle. Okay, so this is the distance between the first one and the middle. Then we do the same for all the others. We take the distance here. And if you call this x2, that distance you can written like this. Then we continue in this way, adding up all the distances. And then we take the average. So after we have added all, we divide by the total number of data in the dataset. And this, what I've written here, is the mean absolute deviation. So each of these are the distances between each data and the average of the dataset, the middle. So if you take all these distances and take the average of those, I get an average distance that the data are from the middle, and that is called mean absolute deviation. So let's take a concrete example of that. So let's take an example of throwing a die 5 times. Let's say I got an 4, 1, 6, 4, and 5. So what is the mean absolute deviation in this dataset? Then first of all I have to calculate the average. So I know where the middle is. So we have 5 plus 10, 15, 20. So in this case we have the average as 4. Of course, it could have been a decimal number also. And then to calculate the mean absolute deviation, we just have to calculate the distance from each of these 5 data from the middle 4. The first one, how far away from 4 is it? Yeah, 0. 1 is 3 away. 6 is 2 away. And 4 is the distance of 0. And 5 is the distance of 1. So now take the average of these 5 distances. I got 6/5 or 12/10. So 1.2. So that means that mean absolute deviation in this case is 1.2. That means that in average, or in mean, each of these data, these 5 data, is at a distance of 1.2 from 4 at an average. Of course, some are closer and some are further away, but at average is 1.2. And this average, that's the intuitive measure, a nice measure of spread or dispersion. But this is not the most commonly used normally. Because of historical reasons and mathematical reasons, the more commonly used is something called standard deviation. And that's the next measure of dispersion we will come to. Standard deviation is probably most used in research and science. More used than mean absolute deviation normally. The intuitive idea behind standard deviation is very similar to mean absolute deviation. So if you have, again, you have the number line here, let's say, take a similar example. We put some x's here representing our data. Like this. Then somewhere here we have our mean, or average, I should say. Then in the last example with mean absolute deviation, or the last measure, we took the distance here. But in this case, we will not take the distance, but we will take the square of the distance. So in the standard deviation, you will take the square. So if you take the first one, we call it x1. And take the difference of the average. And you square this. This here is the square of this distance here. Because when you square it, you remove any signs. So by squaring it, you get rid of, otherwise it could be a negative number here. So this is the square of the distance here. Now we want to find out what is the average of all these squares. So we take the square of the distance from all these data points, and we take the average. So that's similar to how we did for mean absolute deviation. Okay, so we take the average, we divide by n. Then we get something that is called the variance. So this is called the variance. So what is the variance? It's the average of all the squares of the distances. And to get standard deviation, it's called S, it's just to take the square root of the variance. So you take the square root of this. So the intuitive idea here is, if you first square the distance and then take the square root, you will get something similar to the distance. You know, if you take a number, square it, and then take square root, you will get back the number, basically. at least you get rid of the sign here. But so this is intuitive idea. Square it and then take the square root. You get back the number. So you have to square the distance and then take the square root. So this is basically distance. But it's not exactly, because after you square it, you add all up. And first then you take the square root. So it's not exactly, but it's similar to. Okay, so this is how you define the standard deviation. So intuitive sign is similar to the average distance that every data is from the average. Sometimes you see the definitions using -1 here. In a little bit further down, if you study more statistics, there are some advantages of defining like this. But in this first course here, we will keep it simple and we just take n, because it's more intuitive to take the average. But it doesn't matter for a larger data set. If you have a large data set, for example, if n is 1000, then if you take a -1 from 1000 or not, it doesn't change much on the standard deviation. So that's the standard deviation. And this is called, like I said, the variance. So the variance and standard deviation are very similar measures. But it's good to know both names. They're almost the same, but both are used in research and science. So let's take an example of calculating standard deviation and variance. But let's take it simple. In the reality, you should have a larger set, but then it's more convenient to use a computer. So you keep it small here just to show the general idea. So let's take a small data set. 1, 4, 3, 2. So if you're 2. So if you are throwing the die 5 times, for example. So first of all, we have to calculate the average. So this is 5, 5, 12. We have to divide it by 5. So 12 divided by 5. So this is 2.4. Then we want to calculate first the variance, so the square of the standard deviation. Then we have to take the square of the distances. So let's take the first one, 1, and subtract the average. And then we take the second one, subtract the average again, and do the same for all of them. And then we divide by the total number of data, it's 5. Okay, so this is 1 minus 2.4. So this is minus 1.4 squared. This is almost 3, so 1.6 squared. And here we have 0.6 squared. Minus 0.4 squared, this one. And this is minus 0.4 squared. Since these two are same, I could have, of course, written a 2 in front here. Divided by 5. Okay, so 1.96 if you calculate the square of minus 1.4. Minus, of course, disappears. Then you can do it on calculator or algorithm. 1.6 squared is 2.56. 0.6 squared is 0.36. And then 0.016 here twice. And this is 1.04. 1.04. Okay, so we have arrived at the variance is equal to 1.04. If we want to find out the standard deviation, you just have to take square root of this. And if you use calculator on that, we will get 1.02 rounded off to 2 decimals. So we see here that the standard deviation is close to 1, basically 1. That means that the average, intuitively seeing, it means that the average distance from each of these data to the average of 2.4, the distance to the middle, is in average 1. So that's a standard deviation. It's a measure of spread in a similar way to mean absolute deviation, but not exactly. If we would have calculated mean absolute deviation, we wouldn't get exactly the same, but something close to it. But that generally only holds for we have a larger data set. Now we have a small data set, it could vary a little bit. Like I said, historically seen, standard deviation was more used. And the reasons you often hear is that it was before the start of the computers. It was easier to work with standard deviation. Because standard deviation you work with squares. In the mean absolute deviation you work with absolute values, like this. And it was more tricky to use theoretically and for mean absolute deviation. Today, of course, we have computers, so the difference is not so big. But since it has established itself, standard deviation, and also some nice mathematical results corresponding to it, we still stick to it. So that's standard deviation and more used, it's probably fair to say, than mean absolute deviation. So there are some nice mathematical results connected to standard deviation. One of them is called Chebyshev inequality. So Chebyshev's inequality or theory. Yeah, a complete consideration of that is not what we want to do here, but what we look at just one part of it. And it's very interesting because it says that for any data set you have, so for any data set, you know that at least 50% of the data in the data set will lie in the interval. So you take the following interval, you take from the middle, from the average of the data set, and if you go left, square root of 2 standard deviations to the left, and square root of 2 standard deviations to the right. So if you have the data set here, so you have your data set, not rectangular shape, but some shape distributed in some way. You have the middle here. And if you go square root of 2 standard deviations to the left and square root of 2 standard deviations to the right, then it says that at least 50% of the data you should find here in this interval. And further it says that at least 75% of the data you should find if you go out even further, if you go 2 standard deviations. So if you go 2 standard deviations to the left and right, then you have this part. This larger part should contain at least 75% of the data. So if you go 2 standard deviations from the middle to the right and left, and at least 89% if you go out 3 standard deviations from the middle, or the average to be precise. So you go to the left 3 standard deviations, to the right 3 standard deviations. So this is what it says here. So this could be interesting to compare with. So if you take any data set, you know that at least 50% of them should lie here in the middle part, given by this interval. At least 75% should be here in the 2 standard deviations to the right and left, and 89% 3 standard deviations. So you see that standard deviation pops up here quite naturally for any data set. So that's an example of a nice theorem, mathematical theorem, that could be useful also. So that's one advantage of a standard deviation.